Our first example. Suppose there are 25 bacteria in a petri dish, and the number of bacteria doubles every hour. Our first question is how many bacteria will there be in 1 hour? How many bacteria will there be in 2 hours? How many bacteria will there be in 3 hours? And we did a similar problem with the swimming pool bacteria problem. And in this particular problem, you can probably figure this out without too much of an issue, because in the first hour, we're going to double 25 and we get 50. In the second hour, we double the 50 and we get 100. In the third hour, we double 100 and get 200. But what equation do we really need to use to write this function? And we have to think back a little bit. But the key word in this problem is doubles. And if you look back in previous notes, the formula when we have something that doubles, that triples, that quadruples, was something like a b to the x. Whenever we see that, doubles, triples, quadruples have been the words that we've used for these types of problems. But it's been about a week. But a is what we're starting with, so what are we going to put in our equation for a? The 25. The b, what's happening to our problem here? We're doubling. And then we can put this to the x or to the t. Actually, it says after t hours, so let's put t. I think the formula was a b to the x, but it's a variable, whatever you choose to put there. So now that we've got a function written for this, let's use our function to determine the number of bacteria after 6 hours. And the nice part for people who don't have a calculator here is you can figure this one out in your head. I'm not naive to that fact. But in this particular problem, what we're going to type in is 25 times 2 to the 6. So we go over here to our calculator. Y equals, not even y equals, 25 times 2 to the 6. And that gives us our value of 1600 that we typed in. So we've got 1600 bacteria after 6 hours. But it says, using a graphing calculator, let's graph the function from part B. So we're going to go to y equals, maybe. And we're going to type in 25 times 2 to the t. We're not going to type in with the x, that's going to give us a horizontal line. But 25 times 2 to the x, remember that x comma t comma theta n, which is right beside the alpha button. We have to go to the x, there's the x button. And when we graph it, at least we've got a picture in this case. And that's what it says. Use the graphing calculator to graph that part. Well, what does x represent in this problem? Well, we can go back here and think about the fact that x is going to be the time and y is going to be the number of bacteria. So I gave it away here for our answers, but we've got some other things that we can spend our time on. The time. Our input. After how many hours? So it's time. And then the y represents the amount of bacteria. What I want to talk about for a couple minutes here is the window on this problem, because it says on part I, it says, knowing this, what would be an appropriate domain to use for the window setting? And so what I told you before is that I sit down at the kitchen table and I just play around with it till I find something that's going to work for me. The window on your calculator is here. But if you think about it, x in this formula is time. Is time ever going to be negative 10? It's never going to be negative 10. We have 0. That's our first value in our table, but we don't have anything after that. And we've got 1 hour and 2 hours and 3 hours and so forth. So I'm going to leave it as 0 for our x-min, 10 for our max, and our scale of 1. Because it says what would be the appropriate domain to use. 0, 10, 1. Now the thing about using it is, now that I've changed it, look what happens. I can't see anything on the graph. But if we get the appropriate y values in here, amount of bacteria. Well, once again, look at these values here. 25, 50, 100, 200. Are we ever going to have negative bacteria? We're never going to have negative. So I'm going to start at 0. But the values that we have, again, in our table were the 25, the 50, the 100, the 200. What do you think we want to make? And in fact, we found 1600 in part C. What do you think we want to make the maximum value here? Well, I think I want to make it more than 1600. So how about we put in 2000? And this is arbitrary. Somebody else might pick a different number and be fine. Our scale, then, since we're going from 0 to 2000, what would you like to use for your scale? And we don't want to use 1, because it's going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, all the way to 2000. It's going to be very tight on your calculator. But if we change the scale a little bit, our last period class changed it to 100. I actually did 50. But look at our picture. We can see what we need now. And again, what I typed into the window, which I will write down, 0, 2000, and 100. So 0, 2000, and 100 for our scale. And that's really what I do. Look at what you've got and then use it so you can see the picture. And as we go back to our calculator here, part E says use the table in your graphing calculator, determine between which 2 hours the bacteria count will reach 500,000. So I'm going to go to second and graph, which gets us to the table function. Your calculator probably starts at 0. And mine's just been used today, which is why it's not starting there. And I am struggling with it already. But as we scroll down, what we want to find out is, when are we going to get to 500,000? So hopefully it'll be a little bit easier here, but at hour 13, we have 204,800 bacteria. So at 14, we have 409,600. And then at 15, we have 819,200. So somewhere between 14 and 15 hours, and I wish I could scroll that in here. I'll scroll it in for a minute, but if I put it in here, it's going to be very small. Let's see. I'll try it anyway. Using our calculator. You can't see it very well now, but our answer here is between hour 14 and hour 15. In fact, it's going to be somewhere in the 14 hours because it's already at 409,600. So we don't have that much more until we get to 500,000. And the nice thing about using your calculator to do something like that is when we really want to answer the question, which is part F here, write an equation that can be solved to answer exactly what the bacteria count will, exactly when the bacteria count will reach 500,000. We're going to solve this algebraically, and we're going to round to the nearest thousand, which we frequently do. And the equation now, we still have our 25 times 2 to the x. But what that equals now is, instead of y or whatever we put over there, we know the answer. It equals 500,000. And the question is, what do we do first to solve this equation? Thank you. And we do. We divide by 25. When we divide by 25 over here, we get 2 to the x. If you prefer to write the parentheses, write the parentheses. We do not need to have the parentheses in there. If you don't know what 500,000 divided by 25 is, then type it in. And we get 20,000. I hope you don't have to type it in, but some people do. Now that we've isolated the variable, which is in the exponential position, in order to solve this, we're going to put a logarithm on the left side, and we're going to put a logarithm on the right side. Again, without a calculator, this is going to be a tough problem to deal with. Log of 2 to the x equals log of 20,000. And now what can happen here is we're going to take this value of x, and we're going to use our power property and write it as an exponent. So this is x log of 2 equals log of 20,000. And we want to solve for x. So it's x multiplied by log of 2. We're going to divide by log of 2. And when we do, we're going to get our value for x. So we have to type that into our calculator here. Log of 20,000, close the parentheses, divided by log of 2, close the parentheses, gives us our value that we're going to have to round here in a minute. It says round to the nearest thousand. So same procedure that we've been doing. We're going to look at this second 7 here. The second 7. Anyway, second 7. Oh my gosh. I'm giving up on that part. But because that second 7 is 5 or higher, when we round this, we're going to get 14.288 hours. That's going to tell us when we get 500,000 bacteria in the petri dish. As we flip over here, especially for aspiring nurses and doctors here, good problem for you. Suppose for a particular patient and dosing regimen, a drug reaches its peak level at 300 milligrams in the bloodstream. The drug is then eliminated from the bloodstream at a rate of 20% per hour. It says how much of the drug remains in the bloodstream 1 hour after it reaches its peak level of 300, and how much is there 5 hours after the peak level, and round your answers in the table below. Well, We could do this by hand, but I wonder if we go ahead and jump down here to B and let our calculator help us. But the thing that we need to know is, what formula are we going to have to use? And that's going to require us to go back and remember, what's the original amount in this problem? Well, when we take the medicine, we're at full dosage here. We've got 300 milligrams in our system. But as we take the medicine, it's going to wear off over time. We've got a percentage here. It says that, and I need to see my problem here, the drug is then eliminated, that's a really important word, from the bloodstream at a rate of 20%. What's our decimal of 20%? 0.2. And this type of problem here is a percent decrease problem. And when we fill this in, it's going to be the amount over time equals the original amount times 1 minus p, and written in decimal form, 1 minus p to the t. And if we can get that written, we can type that into our calculator and we can fill in a chart. We'll go to y equals, clear that out. By the way, if you are typing in with me, I'm going to go to Zoom 6, which puts it back in this 10 by 10 feature, because we're going to have to figure out our window again. But when we type it in, it's going to be y equals, again, 300 times 1 minus 0.2, close the parentheses, to the x, which is the button beside the alpha button. And we can look at our table, which is going to be second and graph. And I need to scoot back there a little bit. And there we got it. And we can fill in these values into our table. So we see 0, 300. Then we see 1, 240. We see 2, 192. 3 is 153.6. 4 is 122.88. And 5 is 98.304. So there we answered the question of how much the drug remains in the bloodstream in 1 hour. We still have a lot of it in our bloodstream after 1 hour, 240 milligrams. After 5 hours, we only have 98.3-ish in our bloodstream. About 1/3 of it left. But we want to use our graphing calculator here, and the nice part is that we already have it typed in. But we're also asking, what is x and what is y in this problem? Once again, if you go back and think about it, here's x and here's y. So we've got the time, and for our x-axis, and we've got the amount of drug in the bloodstream. So let's say drug in bloodstream. And now, if you type it in and you went back to the original function, notice that nothing's going to show up. So we need to go back and we need to change a couple things on our window. For instance, time is never going to be negative. And In fact, I left everything else on the x's the same. I did 0, 10, and 1. That's going to give us enough. I don't think it's going to show anything here, and it's not. But we have 0, and 10, and 1. And the thing about the drug in the bloodstream is it can be 0, but if you look at the table that we filled in just a minute ago, our highest value is 300, and it's getting smaller every single time. So what do you think we want to make the max value for our y? I'd make it a little bit more than 300. Let's do 400. And the 300 will work. Again, you just sit down at your desk at the kitchen table and you play around with it. In terms of the scale, I'm going to do 50 this time. But on the y's, 0, and 400, and 50, and let's see if we actually get a picture. And we do. Part D. It says, using the table on your graphing calculator, determine how long it will take for there to be less than 10 milligrams of the drug in our system. Well, we have everything in our calculator. We just need to go to second in table. And we're going to scroll through this. And we need to find less than 10 over here in our Y category. So at hour 13, we've got 16 milligrams. Hour 14, 13. There's 10. So where is it less? It looks down here at hour 16 is less than 10. So it's going to take 16 hours for it to be less than 10. And I don't know if any of you have allergies, but that's about the time that I start noticing that I feel like I need more allergy medicine for myself. But now what we want to do is we want to write an equation and we want to figure out exactly how long until we get 10. We already have our equation written. We've got the 300 times the 1 minus 0.2 to the t. But we're going to set it equal to now 10. The thing is, the directions say at the end, do not round any values until the very end. But one thing that we can do, this is 10 equals 300 times 0.8. To make it a little bit simpler there, because 1 minus 0.2. But the reason that we say do not round any values until the very end is because in order to solve this, we need to isolate the variable. So we're going to divide both sides by 300. That's where our first step is. Divide both sides by 300. And if you type in your calculator, 10 divided by 300, you're going to come up with this repeating decimal. We don't want a repeating decimal. So the one thing that I did is I did simplify that fraction, but I'm going to use 10 divided by 300. I don't want to write that decimal down. If you do use 0.03 with a bar over it, you still need to leave this number on your calculator. That's going to be a number you have to use because you don't want to round. But once we do isolate, what we're going to do is we're going to put a logarithm in for both sides. And when we do that, we've got 10 divided by 300 over here, and we have 0.8t over here. And our goal is to figure out the time. Well, we're going to take this value of t, and we're going to make it a coefficient. And we're going to end up then with log of 10 over 300 equals t times log of 0.8. It's t times log of 0.8. Our inverse operation is to divide by log of 0.8. And that's where it's really critical to have the calculator here, because that cancels out. So we have log of 10 divided by 300, close the parentheses, divided by log of 0.8, close the parentheses, gives us our value here of 15.242. And I don't want to round up that 2, that second 2. It's 15.242 hours, URS, hours. But remember what the question's asking here. It says, write an equation to help you solve exactly how long it will take us to have less than 10 milligrams. This is when we have 10 milligrams. So it has to be greater than 15.24 hours to have less than.